Okay, so in this problem what we have is a disk which is rotating counterclockwise at a constant rate of omega, and we're told that link AP is vertical, and that pin P slides within a straight slot which is cut into the disk, and we're asked to let the x, y, z, the lowercase axes, be attached to the disk, and thus rotating with the disk, and we're asked to let the slot be oriented at an angle theta measured from the little x-axis. And at the instant shown, we're told that P is on the x-axis and the x-axis is horizontal. And using this information, we're asked to determine the angular velocity of link AP at this instant, and also the angular acceleration of link AP. Okay, so to start this problem out, let me go ahead and define the two axes. So of course we're going to have our capital X and Y axes, which are going to be fixed to ground. And then we have the lowercase x and y axes, which are already sketched in here in the picture. That'll be, of course, fixed to and rotating with the disk. And what we're going to do, of course, is to try to relate everything here to what's going on at point P. So in this regard, I'm going to start and try to express point P, the velocity of point P, in terms of, in this case, what's going on at point A. And so since A and P lie on the same rigid body, I can use the equation the velocity of point P is equal to the velocity of point A, plus in this case the omega value of link AP, that is the angular velocity of that link, cross with the position vector, in this case of P with respect to A. And so if I go ahead and make some substitutions here, what am I going to end up with? Well, I know velocity of point A is going to be 0. Mega AP is a quantity we're asked to find, so I'll simply say it's in the K. And that could be plus or minus, depending on what's going on in the remainder of the problem. And then R of P with respect to A is simply going to be a distance of minus L, and in this case I can go ahead and write this as capital J. Now I think it's prudent to note that the little k and capital K will be aligned in this two-dimensional problem for all time, so I can change that lowercase k I wrote earlier to capital K. And then if I expand this out here, I'll have capital K cross capital J, which will be minus I. So this is going to end up giving me omega AP times L in the capital I direction. Okay, very good, so that we have that there, that's nice. So we can also then say the velocity of point P is going to equal to the velocity of point O, and in this case those aren't on the same rigid body, we'll want to use the moving reference frame equations. So I'll say plus the velocity of P with respect to O relative to the observer, plus in this case the angular velocity of the rotating frame, crossed with the position of P with respect to O. So in this case here, I'm going to need to make sure I put in my observer, so we know my observer is going to be attached to and rotating with the reference frame, so I can sketch them in right there. And so in this regard, what I'm going to have is the velocity of P is equal to the velocity of O, that's a fixed point, plus the velocity of P with respect to O rel, which is going to be some quantity, in this case along this axis right here. And so I can just write this as, if you would, V rel, and if I want to project that into axes, what I could do here is I could say this is going to be V rel times the cosine of the angle theta in the little I plus the sine of the angle theta in little j. And then I'm going to add to that the omega of the disk, which is, I guess, in this case, just the value omega in the little k direction. And I'll cross that with R of P with respect to O, which in this case is going to be R in the little I. So if I go ahead and expand this out here, I'll have V rel times the cosine of the angle theta in the little I, plus V rel times the sine of the angle theta in little j, and then I'm going to have k cross little I is going to give me a little j, so I'll have plus omega times r in the little j. Now at this juncture it's important to note we have two different expressions for the velocity point P. I have one right here and a second right here, and so we can equate these, and in doing so I'm going to note that at this juncture the little I and capital I and little j and capital J are aligned, and so it's a relatively straightforward process. So in this regard, if I go ahead and look at the little I equation, noting that I can rewrite this capital I as little I at this instant in time, I'll have on the left hand side omega AP times L, and that's going to equal from down below V rel times the cosine of the angle theta. If I equate j components, from the first equation we'll have 0, and from the second equation we'll have V rel times the sine of the angle theta, plus in this case omega times r. So if we look at those, we have two equations and two unknowns, the two unknowns being omega AP and V rel, both of which will prove useful later on, one of which we need as an answer to this problem. So from those we can get numerical answers for these two quantities. Okay, now once we have those, and actually maybe let me write this as a scalar V rel. So once we have those, we can move on to the second part of the problem, which is to look at some accelerations. And basically what I'm going to do here is follow a very similar procedure to what I did with the velocities. So in this regard, I'm going to start out and I'm going to say, well, the acceleration of point P is going to equal the acceleration of point A, plus in this case the angular acceleration of length PA, cross with the position of P with respect to A, then plus omega of length PA, cross with quantity omega PA, cross with the position vector r of P with respect to A. And again, I'll note that since P and A are on the same rigid body, I can use this simplified equation. So if I go ahead and start simplifying this, I know A is a fixed point, so it'll have zero acceleration. Alpha PA is simply going to be alpha PA in a k direction, and in this case I probably should be consistent and make this a capital K. I'm just going up here checking all my axes, we're good. I'm going to cross that with the position vector rp with respect to A, which is minus L in the capital J. I'll add this to omega PA, which is omega PA in the capital K. We found the scalar quantity in the last part of the problem. Cross with, in this case, omega PA in the capital K. Cross with rp with respect to A, which we said was minus L in the capital J. So if we go ahead and expand this out here, K cross J is going to give me minus I, so I'll have alpha PA times L in the capital I. And then here from the triple product, I'm going to have, in this case, plus omega PA times capital K. Cross with, in this case, K cross J is going to give me minus I, so I'm going to have omega PA times L in capital I. Go ahead and go one step further here and expand the remaining cross products. So this is going to give me alpha PA times L in the capital I, and then K cross I is going to give me a J, so I'll have, in this case, plus omega PA quantity squared times L in the J. Okay, now that I have that, I can also compute AP using the rotating reference frame equation. And so let me add a little more space here. I might need that a little later on. So I'll have here that the acceleration of point P is going to equal the acceleration of, the acceleration of point O plus the acceleration of P with respect to O as seen by the observer, plus in this case the angular acceleration of the disk, which I'll simply call alpha, cross rp with respect to O, plus the Coriolis term, which is 2 omega cross velocity of P with respect to O rel, plus in this case the triple product term, which is omega cross quantity omega cross quantity rp with respect to O. So if we go back up to the problem statement here, which I will slowly pan, we'll note that in the problem it tells us that the disk is rotating counterclockwise at a constant rate. That rate being constant will tell me that alpha is actually 0, so this term will go away. And in addition, we know that the acceleration of point O is a fixed point, so we'll have that there very nicely. So if I want to expand this out here, now I'm going to have A of P with respect to O rel, so we know this is going to be along the direction of the slot, so I can call this A rel, times again the cosine of the angle theta in the little I, plus the sine of the angle theta in the little j, plus 2 omega, which is going to be 2 omega in the little k, cross V of P with respect to O rel, which we earlier said was going to be V rel, times the cosine of the angle theta in the I, plus the sine of the angle theta in the j. I'm going to add to that the triple product, which is omega in the little k, cross with quantity omega in the little k, cross with rp with respect to O, which is r in the little I. So we've got a bunch of cross products here to work out, so let's expand this on a term-by-term basis. So if we do that, we'll have A rel times the cosine of the angle theta in the I, plus A rel times the sine of the angle theta in the j. K cross I gives me j, so I'm going to have plus 2 omega V rel times the cosine of the angle theta in the j. K cross j is minus I, so I'll have minus 2 omega times V rel times the sine of the angle theta in the I. And then from the triple product here term, I'm going to do this in one step this time. I'll have minus omega squared times r in the I direction. So again, as we did with velocity, I'm going to note that I now have two expressions for the acceleration of point P, one right there and one right here, and we can go ahead and set those equal to one another and get some nice results. Again, I'm going to note that the little I and capital I axes are aligned with each other at this instant in time.
And so if I do that, if I look at the low lie direction, for example, I'll have that that's alpha PA times L is going to equal A rel times the cosine of the angle theta minus 2 omega V rel times the sine of the angle theta minus omega squared times R. And if I look at the J component, I'm going to have from up above omega PA squared times L, and from down below that's going to equal A rel times the sine of the angle theta plus 2 omega times V rel times the cosine of the angle theta. And if we look at these two equations, what we realize is that we have two equations and two unknowns, and the two unknowns in this case that I'm going to get back are alpha PA, the angular acceleration of link PA, one of the quantities we want to find, and also we can get from this A rel, which will tell me the relative acceleration of the pin within the slot. Okay, I think that just about wraps up this problem. From here it's just numerical substitution, which I know you got under control. Best of luck.